All right, what's going on, guys? So today we're going to be talking about the Hamiltonian for the Klein-Gordon equation now. Again, if you like this kind of content, you can subscribe to my channel. You can visit my Patreon page. I'm also going to be having some notes on this video as well that will be going on my Patreon page. Let's get right into the material now. So hopefully this is going to work a little bit better. I've been getting a couple of comments on my audio that I've been a little bit too quiet. So I've changed a few things up here just so hopefully that you can hear me now. Anyways, so we want to recall that the Hamiltonian for the Klein-Gordon field comes from the space-time symmetries that we talked about while talking about the Legrangian from a couple of lectures ago, or not a couple, but quite a bit ago. And this is what we want to recall. We want to recall that the energy of our field, again, comes from our Legrangian, and we said it looked like this, and that this T00 term looked like this, right? So this is something we, again, derived when we investigated our space-time symmetries of the Legrangian, again, from a while ago. I believe that was around chapter 4 when we did that. Anyways, the energy is associated with the Hamiltonian of the system. If you remember, again, from the lectures during chapter 4, we associated the Legrangian with the difference between the kinetic and the potential energy, and we associated the Hamiltonian as the sum of all of the kinetic and the potential energy. And so in some sense, the Hamiltonian, or in some very real sense, the Hamiltonian is sort of a proxy for the energy, the total energy of a system. And so that's what we have here. Our Hamiltonian is essentially this, right? We can think of the energy as being the eigenvalue also of the Hamiltonian. And that's an idea that comes out of quantum physics, right? So our Hamiltonian looks like this, right? And we have this form right here. And what we really just do here is we plug in our Klein-Gordon Lagrangian in for L and then solve to see what H looks like. And let's do that right now. So if we recall, right, so our Lagrangian looks something like this right here, right? So in here is our Lagrangian. And then here also is the derivative of our Lagrangian with respect to the derivative, right? And so what we're doing here is, so here, I'll just zoom in here a little bit. So we have our Lagrangian, right? So this is L, and this piece right here is right here, okay? And essentially what we're going to do is, this is all just simple math, right? We take the derivative of this guy, right? So we're bringing, oh, sorry, I got lost for a second here. So this 1/2 again came from one of these minus a half of these, which is a half, right? And then we had this right here, which is a half times this, okay? And then we have this right here, and these are getting distributed, our signs are getting distributed, which is why we get the plus signs, right? So in the end, we have something that looks like this, okay? We can now take the 1/2 out, which is all we're doing here. And then we take this here, again, was our conjugate field relationship. So we put that right here. And then we have just this, same thing here, and same thing right here. Now, the thing to recall is this idea that we had an equation or a form or a field that described what this looked like, and that was right here. That's right here, okay? And again, this is the conjugate field to our solution. Our solution is this one right here, is phi. And that takes the form right here. And this is something we also derived, okay? So a lot of this really is not that difficult, right? We had, or I wouldn't say it's not that difficult. It's really nothing new, right? It's, we kind of just we took this right here and we literally just plugged in the Legrangian and we performed all the necessary steps to get to this point right here, okay? Once we get to this point, we can recall now that we had this form for our conjugate field and we had this form for our solution. So now let's take this one step further. So we have H, right? So this was the form of H again, right here. I'll write that down. This is H, our Hamiltonian. And what we want to do now, go back to my pointer, come back up here, is we're saying, okay, so we have H, we have our solution, we have our conjugate to our solution, and so we should be able to calculate H in terms of our creation annihilation operators. This is a long process. Again, this is something that you will see on my Patreon page if that's something you're interested in. I do think, though, that this isn't something that should be dwelled on for too long in a video lecture, because I think we really would just kind of want to hit at the important parts of this. If you want to actually go into the nitty-gritty, I will have notes on Patreon for this, right? So, but the derivation process to get to this point, again, it's long. It's going to be on my Patreon page if that's something you're interested in. But we want to we want to look at this form and just spend a few minutes on this, because notice how it's slightly different than that of these guys. And we can see that it's different in that we don't have these exponentials, right? We don't have these exponentials which have x in them, right? We don't have any exponentials in this form here. And what does that tell us? That tells us actually something pretty interesting. It tells us that our Hamiltonian doesn't rely on space or the x, really, right? We if there's no x in here, there's no x reliance on H. We don't have, for example, this, right? This isn't a thing for this. It doesn't show up here in our equation, right? This is the Hamiltonian again. This sort of gets at the idea of the Hamiltonian as being a very good descriptor of our field, right? Of our quantum field also. And so I'll write this down here. So H has no dependence, we can say, on, all it really depends on are these k's, the value for these vectors k, these four momenta. And so that's something to take into consideration. You can be anywhere in space and time, right? You can be anywhere in space and time. So here's our four-dimensional space. We can think of it like this. And at the entire field, right? The entire field, we have an H, right? Because you can't really go to a single point here. You can't really go to a single point here and claim that the value for H at that point is any different than the value for H at this point. But this is a value for H, and it depends on the values for K, right? It doesn't depend on the value at space-time points. And that, again, this sort of gets at the idea of, if you state a Legrangian, that tells you something about your system, or you can state a Hamiltonian that tells you something about your system. Both of them are very important parts of describing a system, and one of them, as we've seen now, you don't need spatial coordinates to define, and that's something very interesting and perhaps something we might want to keep at the forefront of our minds as we continue with this lecture or with this playlist. And so with all that being said, this is, I'll erase these. With all that being said, this idea, again, of being, of having Legrangian on the one hand, again, the Legrangian, we can recall that the Legrangian looks like this, right? So we had derivatives of phi and phi. And those are what define the Legrangian. So we, in some sense, you don't really have X dependence here, but you have to recall also that phi has X dependence, right? Or has space-time coordinate dependence in it. So in some very real sense, the Hamiltonian can be thought of as more fundamental, right? It's something that doesn't depend on the space or time of the field. And so this is, again, something that we want to just keep in mind as we go forward in this playlist, because I think, at least in my opinion, what's the most fundamental thing that we can postulate when we're thinking about quantum mechanics or when we're thinking about quantum field theory or any field theory is the Hamiltonian. Right? The Hamiltonian is the most, I would argue, the most important thing that you would want to propose when you're proposing a quantum field theory, right? You want to propose a Hamiltonian, and that can get you to every other point of interest as you're studying your quantum field theory or your field theory, okay? The Hamiltonian is king, if you will. And so with all that being said, I hope you guys enjoy this content, and I'll see you guys in the next one. Again, make sure to like and subscribe and visit my Patreon page. Thanks.